like that. It's going to look a bit funny on the video. Oh well. Alright, so assignment 1 will be out real soon now. Maybe. Anyway, it's due at the end of week 6. So find assignment partners ASAP if you haven't got one, and if you want one, you can work by yourself if you want.
Can we form a group of 3?
No. Simple. No. That's what we always say around here. First thing we say is no. Alright, so today we'll talk more about storage, and then maybe next time get on to how we use all this storage stuff to implement relational algebra operations. Alright, so people ask about the quiz. Basically, and I don't even know if this is the order they come out when you look at them. I think it randomly shuffles them, but anyway. So one of the quiz questions that was asked you to come up with some relational algebra that would be likely to be efficient. The basic strategy there was you want to minimize the size of intermediate results, and the surefire way to do that is to do the selections before you do the joins. That will become patently obvious once we start talking about join, for example. For the names of the files, for the tables in the public schema, this is how you get the tables in the public schema. Given the rest of the query, I can't remember what the rest of the query was. And contents of the files in these directories. So some catalogs are global to the entire server, things like PG_database, so they're going to live in that directory. Some catalogs, the catalogue of relations for a particular database, are local, and they could live down here, as do all of the files that represent the tables in a particular database. So the answer was whatever the answer was that said global tables that are related to the server overall, like I said, database, PG_database, PG, I think it's called PG_role these days. Anyway, the user table is also something that's global for the whole server. So those things are up there, and all the other database-specific tables live under data/base/whatever. All right. Assignment 1 is here's a preview, hopefully slightly consistent with what's been developed. So add a new base data type to Postgres. It's very easy to add things like enumerated types and so on. You don't have to do any work at all, just a single SQL statement. But a base data type requires you to do a bit of work. So what we want is to implement sets of integers. And you can write things like that. Notice all of these new base types that you implement in Postgres pretty much all have a literal representation as a string. So all of your sets are strings of characters that look like that. You'll have to convert them, the digits, into numbers, and of course the numbers won't necessarily be single digits all the time. And also it's possible that you might have someone writing braces 1, 1, 1, 1. There should be a canonical representation of that with a single 1, because after all, it's a set. So, one of the functions that you'll have to write, and this will have to be done in C, is to take this string and convert it into some canonical internal representation, which might also be a string, or if you think of some other better representation, you can use that. When you display these things that have been read in, they ought to come out in the canonical form. So if you say insert into some table or other a value which is braces 1, 1, 1. When you do a select on that table, what should come out? It's braces 1. Okay, so that's the canonical form. And we want you to implement operations like containment. So here's a particular integer. Is it a member of this set? Subsets. Is this set a subset of this other set? What's the cardinality of a set? And obviously that's going to be computed by the number of distinct values in the set. And also to allow sets to be used in indexing. If you want to get a head start on that without even seeing the detailed spec of the problem, have a look at that section of the Postgres manual which tells you how to define user-defined types. There's also, in one of the directories, I'll see if I can find it. Ooh, look at that. I think maybe under contrib there might be some examples of defining user-defined data types as well, which might give you a clue. Let's see.
Can you assume that the user who is giving us input is smart user, so he wouldn't
No, they're a complete idiot. All users are idiots. So you have to be able to detect that it's some invalid junk like braces A, comma 312, comma -5. Negative numbers are allowed, but not non-numbers, non-decimal numbers. Off the top of my head, I can't remember where the examples are, possibly under the contrib directory. Yeah, I think if you poke around in there, you might find some examples of implementation of new types. I might be totally wrong. Anyway, if someone can find it, is in there? Good. Right, so it's up to you to poke around in there and find the appropriate things. Right, let's go back to the source directory and sit there until needed. Alright, so that's going to be assignment 1. So while it's not directly modifying the engine, it's writing some code to graft on top of the engine to extend its capabilities. Alright, here's another famous database nerd. And anyone know who it is? Did I release the slides early enough? No, I didn't. If you don't know who it is, you should, because he's probably the most famous database computer scientist in the world, and his name is Jeffrey Ullman. Might ring a bell from the title of one of the books. So he's been a database professor at Stanford forever, published lots of articles, probably a lot more than 200, but the 10 textbooks, and it's pretty impressive, the wide range of areas. So there's a theory, automata type book, there's a compiler book, obviously database books, so lots of and a data structures book as well. So what's he worked on? He's worked on something that was fashionable in the late 80s and early 90s, deductive databases. No longer fashionable, but who knows, they might come back in the same way that neural networks made a comeback. Information integration, so taking multiple different schemas and somehow trying to meld them into a single schema. Information extraction, where you're taking unstructured data and trying to somehow convert it into structured form. He's done quite an interesting system called gradients, which his students have probably taken over the implementation of, but I think he turned it into a company. It was almost tempting to use it in this course. But basically it presents database exercises in a nice way so that each student can be given a totally different set of answers possible. So multiple choice questions, but everyone gets a different set of answers. Computing the possible answers from the database. And he's done some data mining as well. And he's supervised so many well-known database computer scientists as well. So a very influential guy. Alright, what's the chance that this won't work? It did work. Alright, so last time I just got started on the Postgres implementation of the buffer manager. So we talked about generic implementation of buffer managers. So you had a pool of buffers, and associated with each buffer in the pool you had some information like how many people were currently using it, whether it was modified, what page it currently holds, and so on. Right, so Postgres puts all of the information about each buffer pool in these locations here, so you can go and have a look in the source code. And these are some of the data types direct from the Postgres source code. So there's buffer descriptors, which are basically the dictionary. I forget what I called it last time. Directory, maybe I called it. Can't remember. Anyway, it's the thing that contains the data about the buffers themselves. And then the buffers themselves are in another data type called buffer blocks. So basically we've got an array of buffer blocks there. It's the actual buffer pool and the array of buffer descriptors in parallel with that. Each entry in the buffer descriptors array refers to the corresponding entry in the buffer pool. And then there's a data type buffer, which is just used as an index into these two arrays. Well, let me see what's... Oh yeah. Alright, so the indexes, so there's actually two buffer pools that a particular backend can access. There's a global buffer pool which is stored in global shared memory, shared across all of the backends that are currently running. And if on the off chance that multiple backends might be interested in the same table, which if you think about a web application with a database backend, that's quite possible. But each individual backend can also have its own local buffer pool. So positive indexes refer to the global buffer pool, negative indexes refer to the local buffers. You actually set the size of the buffer pool in PostgreSQL.conf. That's the default setting, I think. Is it? Does it 16 times 8K? No, it looks larger than the default setting. In any case, you can't have a tiny buffer pool, but the bigger the better. So as much space as you're willing to expend on the buffer pool will result in increased performance. So there's the directory, there's the actual buffers themselves. This stuff is shared by all of the individual Postgres processes running. And remember that I said what used to be called the postmaster is nowadays also called Postgres, just to be confusing. And an individual Postgres backend can have its own set of local buffers as well. Alright, so more details on where you can find stuff. Data types related to the buffer manager are there, and there, and there, and the code that implements the buffer manager you can find down there. And I think I showed you last time, this README file is quite good. In fact, looking through the Postgres code, look for a README file in any particular directory, especially one that contains a big slab of code that implements one particular module, and you'll probably find quite a nice description of the module. Alright, so what do these data types look like? So how do you identify a buffer? Well, we need to know what relation it comes from. In Postgres' case, we need to know what fork it's part of, in case we happen to have multiple files for a particular relation. And also we need to know which particular page out of the relation file it's actually stored in. And this block number is always relative to the start of the relation, which might, if we do happen to have multiple forks, means we might have to modify it to work out the actual offset within a particular fork of relation data. Alright, last time we had a very simple buffer descriptor. This is what Postgres uses, and I haven't even shown everything. But the buffer tag is basically the ID. Which page from which relation does this buffer currently hold? Buffer flag, see definitions above. I didn't see any definitions above. Interesting. Oh, I wonder where they were. I guess we could spend 10 minutes wading through that to try and find out. Buffer flag, no, we don't have to spend 10 minutes. In fact, because I can do that, and it'll tell me not found. Because, why will it tell me that? What was it called? Go back here. It was called buff flags. Ha, interesting. Is that what I typed? Maybe they've changed the name. I'll just have one. I typed buff flags. Alright, it's called something else these days. That's annoying. They keep changing the names of things. Right, so take that with a grain of salt. The usage count and the reference count, slightly different things. Usage counter combines two ideas, the notion of when it was last referenced and also when it was last scanned. So last time we had very simple buffer replacement strategies, MRU, LRU, and random, which we didn't look at all. So all you need to remember for LRU and MRU is a particular timestamp when the page was last referenced, and you can use that to work out which is the most recently used or the least recently used. In Postgres's case, it uses a replacement strategy called clock sweep, where there are two sets of things going on. There's certainly, you keep a track of when it was last used, not exactly a timestamp, but you also keep track of when it was last examined as a potential victim to be thrown out of the buffer pool. And that's trying, the whole idea with choosing a victim to chuck out of the buffer pool is you want to choose a buffer that's not likely to be accessed again in the near future. How do you work that out? So MRU and LRU are both choices of how you think things might work. This takes into account how often it was used and how many times it's been considered. And if that value eventually drops to 0, it hasn't been used much lately and it's been considered a lot of times to be evicted, so maybe it's about time that it got kicked out. So that's what that's used for. Ref count is the pin count that I talked about last time. It actually stores the index value. And also buffers are linked. There's a free list chain of buffers. So you've got the first free buffer, then the next free buffer, then the next free buffer. It just makes it easier to find things. So when you're searching for a free buffer, and the thing is, really only at the start of the database actually starting up, when you start up the server, that's really probably the only time you've got free buffers. As soon as you start asking a few queries, the buffers are all filled up with pages from various relations. Right, so what does the buffer give you? It gives you an interface, reader buffer. Which one? That particular page from that particular relation. And it'll go and load that page somewhere into the buffer pool. Might need to remove an existing unpinned page, and as I said last time, what happens if there are no unpinned pages? Then you've got a problem. That doesn't happen ever, or at least extremely infrequently in practice. So when you read in a buffer, you increment the pin count for that buffer, and you also increment the usage count. So that's, of course, when you first read it in, that's going to be starting from 0 and you increment by a little bit, by 1. Referencing the pin count, if the buffer's already loaded, then you increment the pin count. If the buffer's already loaded, the usage count might be greater than 0, so it goes up by 1. And what this function returns is an index value into the buffer pool, and doesn't give you back a fork because it assumes that the main fork is what you're after. In fact, you'll find layer upon layer of abstraction in Postgres, and this read buffer thing is actually just a wrapper around the real thing that reads the buffer, which is called read buffer underscore common. And then of course you've got release buffer, where you decrement the pin count. Because we're dealing with systems where things don't necessarily happen absolutely instantaneously. If the pin count falls to 0, it doesn't mean that the page is necessarily not required anymore. We might still be writing it out to disk at the time. So we have to wait to make sure that the buffer really is no longer being used for any purpose at all, and then we can then we can release the buffer.
How do we understand that the buffer is not used for any purposes? Because
there's probably something in the buff flags entry that tells you still being written to output.
Okay.
And that'd be unset. Right, buffer, get a page. It's alright, so what this does, it assumes we've already got a buffer loaded, so we want to get the chunk of data out of the buffer pool and put it into a local data structure where we can start manipulating it. So we'll talk about what a page looks like later, asking whether the buffer's pinned, and when we're doing when we're writing various kinds of logs, we might want to checkpoint. There's also an internal buffer manager function, and all these function headers are dragged straight from Postgres. So if you go looking for them, you should find them. And in fact, I might try it right now just to see if they've changed buffer alloc. Nope, still there. Alright, they may be dragged straight from Postgres, but they may also be simplified a little bit. So anyway, we've got a fork number, we've got a block number, and a relation. Buffer access strategy, in fact, I think you're allowed to employ different kinds of replacement strategies within a buffer pool, and in particular, I think the global buffer pool always uses clock sweep, but a local buffer pool, it might turn out to be more appropriate to use least recently used or most recently used. And we saw last time how certain patterns of access might mess up a least recently used strategy. You know, we talked about sequential flooding. So if you're using a local buffer pool to handle some particular operation, you might have a good idea of how the buffers are going to be accessed, so you might be able to choose an appropriate strategy. Let's see how close I came. Well, yeah, okay. I simplified it a bit. Alright, so it basically can be used by the higher level parts of the system to allocate buffer. Alright, so the replacement strategy that Postgres uses. So we treat the buffer pool as effectively as a circular linked list. So each free buffer is linked to the next free buffer, is linked to the next free buffer, and round. When we get to the last free buffer, it wraps around to the first one, if you like. So there's an index that says, all right, where's the next possible victim? So we don't always go to the start of the free list. So we've got this index that says, all right, let's start here, and then let's start here, and then let's start here, and start here, and go round and round the circular pool. So if a page happens to be pinned, then someone's using it, so we can't kick it out. If a page is useful, as determined by its popularity, which is basically this usage count thing. So every time we use the page, we make a reference to it, we increment the usage count. Every time we look at this page, as we circulate around the free list of the list of pages, we wouldn't care about a list of free slots, because in fact we're doing replacement strategy because all the slots are full. But every time we pass over a page in the buffer pool, we decrement this counter. So if we pass over it a lot of times, eventually that counter is going to fall. And if we pass over it a lot of times and it hasn't been accessed, then that's the kind of page that looks like a potential victim. Alright, so as I already said, if you want, you can allocate your own buffer pool and use a different strategy. Alright, so let's have a quick look. And I was looking at this before and I realised this doesn't really give you a good feel for the way clock sweep works. But so we want to have a look at a buffer pool which only got 3 buffers in. That might be one reason why it doesn't give you such a good idea. And here we've got a nested loop join again. So the requests to open pages, so get me a particular buffer, and the release of that buffer once you've finished with it. So the buffer descriptor entries, let's assume that's what they contain, so that's a subset of what they actually contain, and we assume that we've got these 2 variables as well. Okay, so initially the buffer descriptors look like this. Each one of these is one of them. So initially each buffer doesn't contain any page, so we don't have a tag with a useful value, never been used, not currently in use, and we have a reference to the next page in the list. And maybe the way I described the circular list, maybe that should be 1, so it's a reference back to there. Alright, so we make a request and we'll start looking through the buffer pool, and the first thing we're going to find is a free page right there, so we can allocate that for R0. It's had 1 usage, which is presumably the reason why we requested it, and it's a pin count of 1. Then the next request that comes in is to open page S0. There's a free page there, so we can grab that one and use it for S0. When we release S0, the only thing that actually changes is we decrement the pin count to 0. No one's currently using it. This count stays as it was. The next thing is a request for S1, so there's a free pool, so we wouldn't choose this one to reuse because we've still got a free one and we want to try and hold as many pages in the buffer pool as we can and only replace them when absolutely necessary. So we load S1, we start playing with it, and eventually we release S1, so it also stays in the pool but has a pin count of 0.
Excuse me.
Yeah.
What's the meaning of the free next X?
Oh yeah, alright. So free tells you the first free page. And next is the clock sweep hand. So the clock initially starts at page 1 and all the time this is happening, it actually doesn't move. Eventually, it moves to 2. And you can see the free list vanishes pretty quickly. Right? So the free list starts pointing at page 1, then points at page 2, then points at page 3, and then is gone. And that's pretty much what happens when you start a database server. Initially the buffer pool's empty, you ask one query, on a decent sized relation you'll fill all the buffers in the pool with all the pages from that relation. Alright, so the clock hand has moved to the next item, to the next buffer pool, next buffer in the pool. What's the next request? We request S2. So since the clock hand was pointing here, that's the page that we choose, and because it has a low usage count, in fact everything's got a low usage count, and that's why this example is a little bit crappy, because nothing ever really gets a high usage count. But in any case, that's the one we choose. That stays there. S2 gets loaded into here. Eventually we release S2. That becomes empty, becomes unused. Then we release R0. That also becomes unused. The clock hand still doesn't move. It just lingers. But eventually you can see that it's going to move to the next buffer in the pool. Alright, so we do a request of S0 again, alright, which was not in the pool before. So the clock hand moves along and we decide this is the one we're going to take. So that becomes, contains S0. When we then release S0, the pin count goes to 0, and unfortunately this doesn't really show clock sweep in action very well. You can see that the clock hand has moved to 3, then it moves around to 1, but unfortunately the way the request and release patterns work, the usage counts never get above 1. But anyway, that's the idea. We've got this clock hand that moves around the buffer pool, and each time it looks at a page, it decrements its usage count. If the usage count falls to 0, that's a potential victim, and that's the one we kick out, as long as its pin count is also 0. And apparently that's a better strategy than either plain LRU or plain MRU. And if you really wanted to, you could change the buffer replacement strategy in Postgres and measure. And there is a way of actually getting buffer statistics, which I can't remember off the top of my head, but you can. So if you really wanted to check whether clock sweep was any good, you could run a query with clock sweep, and then you could go back and you could change the default strategy to LRU, and then run it again, and you could see the number of hits and the number of misses and the number of page reads and writes to see that it had done better. Now when you're doing analyses like this, you need to be a little bit careful. You wouldn't want to start your server up, ask a query, ask a few more queries, and then look at the hits and misses, and then create another buffer pool with a different strategy, and then run the same set of queries. That was a crappy example, but anyways, the point I was trying to make is that the results that you get from the only way to get consistent results is to start from a newly executed backend, because you got the buffer pool completely empty. If you start after the server's been running for a while, the buffer pool contains stuff and you don't know how that stuff's going to interact with the query that you ask. So if you really want to do comparisons like that, always you've got to start from, you've got to restart the server each time to run the comparison. All right, so the buffer pool allows us to fetch particular pages from the files of the relation. What do those pages actually look like once they're loaded? So all of this stuff basically fits in around about this area. So we've talked about buffer management. So the page management and the tuple management is a layer effectively on top of that. It interacts with the buffer and it supplies information to these higher level operations. All right, so the database applications see a table as a collection of tuples, but we know that physically they're actually done as a collection of pages where each page contains a certain number of tuples. And tuples and records, I use those terms interchangeably. So you can actually identify a tuple by an ID, which tells you which relation, which page in the relation, and what the offset of the tuple is in that relation. So is it the first tuple, is it the 30th, is it the 100th, and so on. So it's not really an offset, as we'll see. It's actually an index into some other table within the page which tells you where the tuple really is. So the disk and buffer manager give us back a sequence of blocks accessed by page ID. So how do we organise space within the page? When you get down to it, a page is just a big array of bytes, 8K bytes in Postgres's case. We need to be able to interpret it as a collection of records. So we need to know where all those records are. We need to know if there's a chunk of bytes in the page that used to hold a record, but that record's been deleted. All this kind of stuff needs to be managed, and it's managed at this level. So there can be a request page operator, which, as we just saw with the buffer manager, goes down to the buffer manager and asks it to load the appropriate page. Once we've loaded a page, we then might want to get records from within that page. So there might be a get record function to do that. We might want to insert records, update records, and delete records. And the record ID, the reason why I've just written record ID in some of these ones where you might say, what about the page containing the record? Well, the record ID contains a page ID, so we don't need to put it as an explicit parameter. So how we structure the internals of a page depends a lot on the kind of records that we're storing in the page. Are all the records the same size? That makes it really easy to manage the space within the page. Can records be different sizes? That becomes a bit more painful, because then you've got the task of managing arbitrary size objects within a fixed chunk of data. How do we manage free space? And possibly even, so we know that a page is 8K bytes. What if we have a very large attribute value that needs to be stored, something larger than 8K bytes? Obviously it's not going to fit in the page, so perhaps it has to be stored somewhere else. So we need to keep track of things like that as well. And also when we start doing things like hashing, the hash might tell us this record belongs in this, we're trying to do an insert, we do a hash, this record belongs in this page, but this page is full. We need to effectively extend the size of that page, and the way that you do it is you'd have another file containing additional pages, and you'd link this page in the main file to a page in the overflow file, so that effectively you can make pages arbitrarily large, even though a page is fixed size 8K bytes. Large data value stored elsewhere, that's what I I was talking about before. We have a toast table, and I looked up the meaning of toast the other day and probably forgot what it was. I think the first T is the oversized attribute storage technique might be what it stands for. So how do you deal with attributes that are too large, attribute values that are too large to fit within a page of tuples? And so that'd be one way of doing it. So what you actually store in the tuple isn't the value itself, it's a reference to the value. So you could put something like a record ID, is that right? The oversized attribute storage technique, wow, what a miracle. So yeah, so if you got, in the case of a toast table, in the case of a toast attribute, what you actually store in the main data page, in the, you know, in the main fork, is a reference to the value in the toast file. So that's going to be something similar. It'll say which page in the toast file it is, and whereabouts in that page the value starts, and how long that value is, because typically it's going to be quite long. Another way of handling that, rather than having a toast file, is to actually store the tuple in the page, and hey, if it doesn't fit, we've got to stick the rest of the value into a separate page, and that would be an overflow page. So how we implement pages depends on a whole lot of things like that. Right, simple case, well, it seems simple at first glance. If all the records are the same size, then we just treat the page like an array of records, and so the first tuple we insert goes in that slot there, the second tuple goes in that slot there. All the slots are exactly the same size. The only thing that we really need to keep track of is how many of them that we've stored into the page. So we need an additional piece of information within the page itself that says how many tuples are there. Of course, this cuts into our storage space, so we're going to be able to store one less tuple than we might otherwise have done. The other thing about this is a packed data structure, so all of the free space is down here. An alternative, and we'll see why this is a better alternative in the middle in a minute, is we've still got slots, but when we come to delete a tuple, we don't necessarily have to do some kind of compaction, which is what we have to do here to keep a single chunk of free space. What we do is we simply tag that slot as being unused. Two possible ways that you could do that. One would be to have, as part of the record, some kind of flag that says yes, this record is valid, or no, it's not. So you could do it that way. An alternative strategy might be to have some kind of bitmap at the start of the page that tells you which tuple slots are actually in use. So this one tells us that tuple slot there is in use. This 0 says that one's free. This one says that one's in use, and so on and so on. Once again, this is chewing up space in your page that is no longer available for tuples, but at least if you're dealing with a bitmap like this, how many tuples in a page? 100. So that's only 4 or 5 words of data, 100 bits. So that's not too bad. Right, so given, so where do fixed size records come from? They come from table definitions where all of the attributes are fixed size. So it's pretty easy to come up with examples of fixed size records, pages. Right, so here's an example. There's a sort of bogus one, but I'll start with one that's slightly more realistic. So imagine if we got a university database and we represent information about courses. We've got a unique ID, that's an integer, that's 4 bytes long. We've got a course code like COMP9315. At UNSW, that's guaranteed to be 8 bytes long, so that's what we need to store. We might want to store units of credit available in the course. That can be an integer. In fact, it can be smaller than that because we don't have anything larger than 24 unit of credit courses. And in fact, once terms start, we probably won't have anything larger than 18. So that could be stored in a lot less than 4 bytes, but you know, we've declared it as an integer, so that's what we put up with. And if for some unknown reason we wanted to store the average mark in a course, we could store that as a floating point value, which once again would be a fixed size. How big is it? Depends on how your database decides to represent floating point values. It could be a 4 byte quantity, or it could be an 8 byte. And you know, maybe we could even have something like something that I should have had was which term is the course offered in, and that could be done as something like 18S2, which once again could be a fixed size. Or whatever. So that could be one way of doing it. Another way of doing it might be to have a foreign key referring to another table which describes all the terms. A foreign key is likely to be an integer value which is 4 bytes long. So all of the fields here are fixed size. So the records in this course table are all going to be the same size, which happens to be 4 plus 8 plus 16, 20. Let's assume a float is 4 bytes, so 24 bytes. Every record of this type is going to be 24 bytes long. Let's have a look at a slightly more realistic version of that, where if you're someone like me, sure, you work with course codes all the time and you understand when someone says pick a random course code. See, I know that's software construction, but people might want to know what the title of the course is. So we put in the course title. Now, course titles are strings and they're highly variable in length. So these kind of records, despite all of these other attributes being fixed size, have a variable size component. So these kind of course records are going to be differing in length depending on how long the title happens to be. So what are the common features? So all of the attributes have to be a fixed size. That's kind of obvious. As soon as you throw in an attribute like a varchar, then you don't any longer have fixed size records. All right, well, getting back to those page formats, how can we implement these kind of operations? What's a suitable data structure for representing a page? A function to insert a new tuple into a page, and a function to delete a tuple from a page. And I'll do that after the break. So let's